Hi, I'm Sarah Gibson, and I'm going to be talking today about how we can establish flux rope chirality using white light polarization data from the PUNCH mission. So the polarimeter to unify the corona and heliosphere, or PUNCH, is a small explorer mission that has been selected by NASA for flight. PUNCH studies the young solar wind, which is the region where the corona gives rise to the heliosphere and solar wind. One of the primary science targets for PUNCH are coronal mass ejections, or CMEs, and these are generally expected to incorporate coherently twisted magnetic fields, or flux ropes. PUNCH provides the full field of view from pole to pole using 4 synchronous smallsats. It fills existing gaps between coronagraphs and heliospheric imagers and allows unprecedented observations of the evolution of CMEs from sun through the solar wind. In addition, PUNCH obtains polarized brightness measurements, which when used along with brightness white light measurements, are a powerful tool for imaging and localizing CME substructure and the evolution of it in transit. Until now, only the coronagraph data close into the sun has had this capability, and it has had limitations on the sensitivity needed to fully exploit the polarization diagnostic. PUNCH is designed with the sensitivity, the spatial field of view, and the polarization capability for both inner coronagraphs and the 3 heliospheric imagers that surround it. So why is polarization important? Well, let's consider a blob of material or an object. And here, this is the viewer looking along the line of sight through it. This is the sky plane. One possible mapping of the white light structure, the one usually used for the close-in coronagraph data, would be to project onto the YZ sky plane. Further out, it's more common to map the structure onto an azimuthal equidistant map, like a fisheye, with grid spacing constant in epsilon, which is the elongation angle shown here. But anyway, in 3D Cartesian coordinates, y and z can be obtained from the position of the feature on the map projection. And then it's just a question of establishing where the structure is located along the x-axis, which is where the polarization ratio comes in, because it can be directly related to the scattering angle of light off the object. In particular, PUNCH's polarized brightness and brightness gives that ratio, and that in turn specifies chi, which is the scattering angle. And so chi comes from the polarization. Epsilon is the elongation angle observed from the sky projection, and that means that the out of sky angle can be determined from these other angles. And then after that, it's just more triangles, factoring in the distance from the sun and earth, and we get the 3D position of this blob in 3 dimensions. One final comment before I leave this slide. I've drawn here the so-called Thomson surface, which is significant because the Thomson scattering, which gives us our white light observable, is maximized there for the simple reason that the scattering angle chi is 90 degrees. Now near the sun, the Thomson surface is co-located with the plane of the sky. But then for wider angles, since lines of sight are not parallel, it occurs along this spherical surface. Now, of course, with white light, what we're looking at is optically thin material. And so we aren't generally considering a point-like structure, but something more distributed. To explore this, let's consider a Poisson-type CME, a hollow shell of density. And this is a model by Hugh Morgan, which has been incorporated into the Forward SolarSoft package. This lets us introduce non-localization in a simple way and build some intuition. And in this way, when lines of sight pass through both near and far sides of the shell, it means that the polarization ratio is actually diagnosing the center of mass between these localized structures. So let's start with a line of sight at low elongation, intersecting the plane of sky close to the sun. There's a tiny little CME here with an apex position shown by an orange dot. Now, this is giving the ground truth from the Poisson model of the position of density center of mass. The color blue-red is showing that the bottom is a little bit farther from the plane of the sky, closer to the observer, than the top. When we do the polarization analysis, forward modeling the white light PB and B, we recover the position very well indeed. But there's an important caveat. Because there are 2 solutions to the scattering angle chi, there are actually always 2 possible solutions to the AS position, to the position of this superparticle, when we do the polarization analysis. And one will be in front and one will be behind the Thomson surface. For this small elongation angle close to the sun, this means we won't know if what we're looking at is in front or behind the plane of the sky. It's a front-back ambiguity, but it's one that can be largely resolved. For example, if we see the CME source on the sun, on the near side of the sun, which would then imply that the CME is coming towards us along a plus X trajectory. But even without source information, the time variation can also be used to eliminate the so-called ghost solutions and establish the direction of the CME. So let's look at what happens as the structure expands and things get a little bit more complicated. For the bottom part of the CME, the localization, this is the ground truth again, of the center of mass is still pretty good. Here's the polarization front solution. But for the top, which is, as you can see, nearer the Thomson sphere, it's not as good. And this is because some of the CME has actually moved beyond the Thomson surface. And for such points, like this nadir position, the solution at the front of the Thomson surface has become the ghost instead of the back. And when we look at the back solution, we can tell something is going on because it has lost its spatial continuity. When it was close in, it was all red, but now some of the material that used to, and red means behind the plane of the sky, but now the stuff that used to be behind the plane of the sky is now moving in front of the plane of sky. It's getting bluer. Now, if the CME were actually moving away from the observer, that would not make sense. So to summarize, if we have a CME moving toward the Earth, the front solution and the position of the front solution is going to stay positive. It's actually going to get more positive with time. The whole structure will continue to get bigger with time. And this is what we would expect for a CME coming toward us. Whereas the back solution will start out negative or red, but parts will get more positive with time, and it will ultimately transition to positive blue mixed with red. And that's not consistent with what a CME, if it were in fact a back solution expanding away from us, would do. So it's going to be clear which one is the correct trajectory and which one is the ghost. If we have a CME moving away from the Earth, the back solution down here will stay negative, red, the whole time, and all points will get more negative with time. And although it will get bigger at first, this image is going out to a field of view of 7.5 solar radii, and this goes out to 75. But then this and this one are both with a field of view of 75 our sun. And so it's not continuing to get bigger, it's asymptoting. The front solution, the other thing is when we solve for the front solution, we'll get the exact mirror of the back solution. And that's because there's not any weird crossing of the Thomson surface because it's moving away. So this is very different behavior than a CME coming toward us, and it'll be clear which one is the ghost. But let me comment that close to the sun, it will be less obvious. So just looking at a coronagraph, for example, front and back, they'll look the same for both the Earth away and the Earth toward. It's really when the CME gets out into the heliospheric imager field of view that things get clearer, assuming that there is a structure bright enough to track. And so the PUNCH wide field imager, those are the heliospheric imagers, the 3 satellites, they've been designed with very high sensitivity for exactly this purpose, and of course, the polarization that allows this analysis. Now, the more localized a feature is, the more straightforward it is to determine the position in 3 dimensions. CMEs are generally good because they're brighter than what they're moving through, and the bright front can be used to map out a trajectory, as I've been describing. But CMEs also have substructure. This is the classic 3-part structure, front, cavity, and core, that's been used as evidence for CMEs as flux ropes for a long time. So using polarization ratio in stereo A's Core 2 coronagraph data, which has polarization data, the position of the front and the core were mapped in 3D and then reprojected into the SOHO plane of sky. Because of course, if you know it in 3D, you can change your viewing angle and say, what would it look like? And since SOHO and stereo were at different longitudes, this was a very interesting test. And in fact, the structures matched the ones observed cotemporally between stereo and SOHO. Which brings us to the third part of the talk. If the core is showing mass within the flux rope, can it be used as a trace of flux chirality? Well, yes, if we know what to look for. In particular, it can be shown that a structure that's curving clockwise back to front on part of the structure is evidence of left-handed chirality. And just to demonstrate that, these are just left-handed and right-handed screws. And you can see if you follow from back to front, this is curving clockwise. But if you go back to front on the right-handed screw, it's going counterclockwise. So using that same feature that I just showed in the previous slide, DeForest et al. Plotted the distance into the foreground, so going back to front, and compared it to the distance along this C curve, and showed that these points 3 to 0 are going back to front. And so that means it's going counterclockwise back to front, and so it's right-handed twist. And this particular CME was later observed as a magnetic cloud, which also showed right-handed twist, consistent with what was deduced from the polarization data. So let's look at this with forward models now, in particular going back to the Morgan-Poisson model, which has a parameter that can be used to incorporate an overall twist of the croissant of the CME structure. And these figures are showing the model ground truth three-dimensional position of the center of mass along the line of sight, as I've been showing all along, but this is showing you close to the sun, within 5 solar radii. And this is a case where there's a CME moving toward the Earth, but along an oblique angle. And we're looking at it as though we were looking from the Earth. So since the CME is always in front of the plane of the sky, in this case, I'm not using the blue-red color table, and I'm using an intensity scale where back to front is shown dark to light. And so on the right, we've got the front polarization solution, and on the left, we have the ground truth knowledge of the weighted line of sight center of mass. And you can see that the front solution, polarization solution, is capturing the 3D location well. But it's perhaps not obvious what the chirality is because this is a compact structure near the sun. So just as in the case of the trajectory, which became easier to deduce as the structure moved out into the heliosphere, as it moves out and expands, it becomes easier. And now it's clear that it's curving clockwise from back to front, or dark to light, both here in the ground truth and also in the solution obtained from the polarization ratio. And that means it's a left-handed flux rope, and that's captured by the forward modeling and the deduction of the polarization. This kind of an oblique view is helpful for resolving the circulation, but it should be noticed that if other views, for example, looking down perpendicular to the axis of the flux rope, can be potentially ambiguous or even misleading. And this movie is meant to illustrate that. It shows a left-handed and a right-handed twist, returning to the red-blue color table now. And on the left, we've got the left-handed, of course. When we view it obliquely, like for example there, then the direction of circulation is clear. But when we view exactly perpendicular to the axis, like for example right there, things get a little bit confusing. And this basically makes the point, taking the left-handed twist and showing 2 snapshots from its movie. On the left is the oblique view, and you can see we've got a circulation about the axis from back to front, red to blue, clockwise, left-handed. On the right, however, this is the view exactly perpendicular to the axis. And if this was misinterpreted as being a view aligned with the axis, it would appear to be rotating counterclockwise back to front, red to blue. And then the prediction of the chirality would be wrong. But the crucial point is that polarization data provides 3D location of a feature. So it can be rotated, and such ambiguities can be cleared up. So to conclude, the 3D position of CME structure is well captured using polarization analysis for small elongations close to the sun. There is a front-back ambiguity, which either requires information about the source or tracking of the structure versus time. And this is also, and the polarization presents a tool for distinguishing between left-handed and right-handed CME flux ropes. However, the view perpendicular to the axis can be ambiguous. Luckily, 3D realizations of the feature allows rotation to an unambiguous viewpoint. Punch is designed with the sensitivity, field of view, and polarization capability to undertake these types of analysis throughout the heliosphere and provide new observational clues to the trajectory and chirality of CMEs. Thank you.